get started. Okay, so our last chapter here that we're looking at is chapter 7. And this one, gets into conic sections. Now, basically, when we're talking about, conic sections, we're talking about what happens when you take a double right circular cone and, basically run a plane through it. So you can see you have your double right circular cones over here. And then depending on which angle that plane makes with those double right circular cones, you get different shapes. Just 1 minute, guys. Okay, Tiffany, I'm really sorry to hear that. I hope everything goes well. And if you need to leave, that's totally understandable. So thank you for letting me know and feel better, okay? All right, guys, so as I was saying, so you can see the 4 different shapes that you can kind of create when you have, the double right circular cones with the plane. So you can see when the plane crosses just one of those cones at an angle, we get a parabola. If your plane is going to be, perpendicular to the vertex of the cone, where those 2 cones meet. So if it's going to be perpendicular to that, you're going to get a circle. And then, just from that circle, if you make a little bit of an angle, you get your ellipse. And then, of course, you can see in the last shape where your plane intersects both the top and the bottom cones, you end up getting a hyperbola. And if you actually click on this image, it actually takes you to a video where they, it's an animated video where it kind of shows you how the different shapes are created. And it gets a little bit into the geometry behind it, the angles, and all of that also make a difference in, what kind of shape you are going to get. So if you just click on that image, it will take you to a YouTube video for that. Now, we have talked about parabolas, of course, in this course. We've done parabolas in chapter 2, chapter 3. We've talked about all the different characteristics and properties for parabola. But as I said, we're kind of looking at this in a more geometric sense. So we talk about the parabola, but we also want to discuss where the focus and the directrix for a parabola is going to be. And basically the idea is, you can see in the red is your parabola. You have your vertex of the parabola, which is either the lowest or the highest point on your parabola, depending on, if it's opening downwards or upwards. So the distance from the vertex to the focus and the distance from the vertex to the directrix is always going to be the same. So basically this distance is always going to be the same. And that's kind of what they're talking about here in the definition. They're saying a parabola is a set of all the points in the plane that are equidistant from a fixed line, which is your directrix, and a fixed point, which is not on the line, because, obviously the focus is not on the parabola, it's away from the parabola. Now, this idea of the focus is really interesting because, when we talk about the reflective properties of the parabola, that focus will come into play. Now, of course, we're keeping the same equation for our parabola. So you have this one here, what I call as the transformation form, but, of course, you can have that in the standard form also, which is what we are, familiar with. So that part does not change, but they are introducing some new formulas here. So, that line for the directrix can be defined as y equals k minus p. The ordered pair for the focus, the points are defined as, h comma k plus p. And then remember, we use hk for the vertex. And of course, those h and k values are coming from your equation of the parabola itself. We define this value of a as a equals 1 divided by 4 over p. So it's basically 1 divided by 4p. And this value of p is actually that distance between the vertex and the focus, or the vertex and that directrix. And so that's how they are using, that distance of P. And remember, since your focus is same distance from the vertex as the directrix is, that's why we are adding and subtracting that P from the K value to, move it up or down depending on how your parabola is opening. And you can see in both of these images over here, what your graph ends up looking like. If your parabola is opening upwards, then the directrix will fall below the parabola. The focus falls on the top. If your parabola is opening downwards, then of course the directrix is on the top and the focus is going to be below the parabola. So you've got some examples for that. You can kind of take a look at, how to calculate the equation if you know the focus and the directrix, or if you have the equation, how do you find your focus and directrix? So I've included those examples in your lecture. You can also have these parabolas opening left and right. And, if it's a parabola opening left and right, then of course the equation of your parabola will change a little bit, which means it will also affect, the equations for your directrix and then the ordered pairs for your focus also. And you can see the vertex will still stay in the same order because it's always X comma Y. So the vertex is still H comma K, but some of the other values will definitely change. So you can take a look at those. But this is kind of what I wanted to show you additionally is that reflective property I was talking about. So what happens with this parabolic shape over here is, imagine if you have a light, or for that matter, a sound source over here. So what's going to happen is those light or sound waves are actually going to reflect off the surface of the parabola. So you can see this is where, those waves are coming from. And they're going to bounce off that parabolic surface, and you will see all of those waves end up concentrating at the focus. So all of them are going to end up right here at the focus. So, think about those satellite dishes, something like for Dish Network that you put, at your home. It's the same concept because that surface of your satellite dish is a parabola, and, where they place the receiver, that's where basically, they're getting those sound and light waves. And, then of course it transmits to your television. This property is actually used in a lot of different objects. So you can see some examples over here. We're talking about a telephoto camera lens, radio antennas, like I mentioned, satellite dishes, eavesdropping devices, which kind of works, of course, like your satellite dishes, and even something as simple as a flashlight. Okay, Sarah, not a problem. That should be fine. Try that. And, of course, we try to use that same reflection property for a parabola in telescopes also. So depending on, what the mirror that has been placed inside your telescope would look like, based on that, they'll calculate where the focus should be. And, that's kind of where the light from the distant planet will be coming in. So again, you can see the light comes off, bounces off that parabolic mirror, and then it's going to go towards the focus. And normally that's where, we would place the eyepiece for the telescope. So then, of course, you get a great image of whatever planet or star you are looking at a distance. So just some different properties. So this will be, like I said, you have studied parabolas in previous chapters, but this one is just looking at it in a little bit of a different light, with this idea of a directrix and a focus, but, of course, a lot of it will seem familiar. So this is the first conic section that we look at. Then we get into ellipses and circles. So basically what happens is, as you can see over here, they're kind of demonstrating how you can draw an ellipse. So you can attach a string to, 2 nails, or this looks like tack pins, and then just run a pencil around, and it gives you the shape of the ellipse. And the place where you attach those 2 nails or tack pins actually are where the focus of your ellipse is going to be. So again, a very interesting reflective property for ellipses also. If your light or sound source is placed at one focus, it's going to bounce off that elliptical surface, and all of that sound or light is going to be concentrated at the other focus. So the light source or the sound has to be at one focus. It's going to reflect off that elliptical surface, and then it's going to concentrate at the other focus. And again, you can see the definition for an ellipse here. We're saying it's a set of points in a plane such that the sum of their distances from two fixed points is going to be constant. So they're basically saying if you take the distance from the two fixed points, which is your focus, and add them together, depending on which point you pick, those distances are always going to be the same. It's going to be constant. And like I said, those fixed points are called focus, or the plural is foci or foci, depending on how you want to say that. So this idea of a reflection property, one of the examples you can think of is, a dentist light. If you're in the chair, they pull that light towards your mouth. So that would be the dentist light that they're talking about, because they can get a concentration of light, to focus it around, the mouth, the place where they're working at. They actually also have these things called as whispering galleries. A lot of different places have that, but there's definitely one in Washington, D.C., in the U.S. Capitol building. So like I said, it's the same idea, because the ceiling is an elliptical ceiling. So what happens is if people are standing here at the focus and speaking, nobody, anywhere else can hear what is going on. But once the sound bounces off that elliptical ceiling, anybody who would be standing here at the second focus would be able to hear that conversation, just like the people were standing next to them. So it's pretty neat how, these reflective properties work out to be. Another thing, of course, satellites and moons and this Earth around the sun, all of them form this elliptical path. So in our case, the moon or even the satellites that we launch, or, like they're talking about Hubble Space Telescope here, they actually use the center of the Earth as one of those focus points. And then based on that, they can create, what that elliptical orbit around the Earth should be, and placed on that, because, of course, there are so many satellites up there. You don't want them running into one another. And so, they're going to, each one will have a different elliptical path. But again, they're using the same concept of an ellipse to, create those paths around our planet. So the equation, for the ellipse, because remember how they told us that the sum of the distances are constant. So you will actually have, as you can see over here, it's an addition formula. So in this case, again, these are our two focus points. So we call them positive C and negative C. And of course, as ordered pairs, they are C0, negative C0. The longer axis is what we call as the major axis. So that goes from point V1 to V2. So that's your major axis. The shorter one is called the minor axis. The endpoints of these are called vertices. So you have, small letter b and negative b will be the vertices of the minor axis. They don't have this in your image over here, but the vertices for that major one should be negative A0 and positive A0. So those points will become the vertices of the major axis. And, if your ellipse is centered at the origin at 0, 0, then these points, as you will notice, end up becoming your X and Y intercepts also. So the points positive A, negative A become the X intercepts. The point positive B and negative B will end up becoming your Y intercepts. So depending on if your ellipse has a horizontal major axis, which is what we saw in this image over here, with the center of your ellipse at 0, 0, the equation for our ellipse is going to be x squared over a squared plus y squared over b squared equals 1. This relationship is something you will need to remember because it changes when we go from an ellipse to a hyperbola. So you will need to know what this relationship is. So remember, this is with the ellipse. Your focus points or foci are at C0, negative C0. Like I said, your y-intercepts are at 0, B, 0, negative B. And if it helps, you can think of your x-intercepts at A0, negative A0. And then if your ellipse has a vertical major axis with the center at 0, 0, so that would be this guy on the right. So if your ellipse has a vertical major axis, you should see the difference between the equation on the top and this one. You will see how those denominators end up switching places. So now you've got x squared over b squared plus y squared over a squared equals 1. Same relationship between our a, b, and c variables. Your foci will now be on the y-axis, so you will see how the ordered pair has changed. It's now become 0, c, 0, negative c, and look at the foci here when it's horizontal versus the vertical. Your x-intercepts are now b0 and negative b0, which means your y-intercepts are now going to be 0a and 0, negative a. So, of course, as you change the direction of your ellipse, a lot of these points will end up switching places. And then, like I said, your equation also ends up changing. So the best thing I can tell you to remember by looking at an equation, if you have a horizontal or a vertical major axis, the larger denominator is going to be underneath the variable that represents the axis. So in this case, since it's a horizontal major axis, your larger denominator is going to be under x. When it's a vertical major axis, your larger denominator is going to be under y squared. So you can see some examples. Okay, like this one over here, you will see how your larger denominator is under x squared. So that means this will be a horizontal major axis. So your ellipse will be, horizontally oriented. If you see the larger denominator under y squared, then that means it's going to be a vertical major axis. So that's the easiest way for you to tell, what kind of ellipse you are looking at. Now, both of those examples that we looked at were, with the center being at 0, 0, but you can have where the center has moved, kind of like we talked about with circles in chapter 1. So you can see when your center moves, your equation changes a little bit. So, now we are introducing those h and k values, kind of like you have with those parabolas. Yeah, like how we have the vertex hk and the h and the k are reflected in the equation of your parabola. It kind of works in that same way. But, of course, that's a parabola. This is an ellipse. So when your center is not at 0, 0, this is kind of what your equation would look like. But it's still going to be the same idea. Since the larger denominator is under the x value, this will still be a horizontal major axis. Now, we talk about, the circle being a special case of the ellipse. Because just imagine, like in your mind visually, what happens if you take those two focus points from an ellipse and bring them, together? So just start moving them towards each other. And when those two focus points will overlap on top of each other, that ellipse is going to shrink and it basically becomes a circle. And so we think about the circle as being a special case of the ellipse. Now, circles, you have actually done all of these examples in chapter 1. So you've actually had a little bit of a heads up on this part. So this should look familiar. This is the equation of your circle when it's not centered at 0, 0. If your center is at 0, 0, remember, you don't have to put those h and k values. So you just have x squared plus y squared equals r squared. So this is when your center is at 0, 0. But when the center is, at any other point, then this is what your equation ends up looking like. And your radius is the distance from the center to the circumference. So that's always going to be a positive distance. So center at hk, and then of course your radius is r. So all of these examples you have gone through with chapter 1, but again, you can find, the solutions to this or how to solve them in your video lecture, so you can take a look at those. So those are, 3 out of the 4 shapes from your conic sections. And then the last one is that hyperbola that I was talking about. Now, the way we define a hyperbola, we talk about it again as a set of points in a plane, but this time it's the difference between the distances from your 2 fixed points that is constant. So this is actually a difference. And remember, the ellipse was a sum. So that's actually how you can tell the difference if you are looking at an ellipse or a hyperbola, because their equations look kind of similar, but it's the difference of this ellipses have a plus sign in the middle and your hyperbolas will have a minus sign in them. So let's talk about the reflection property before we get into the equations. So with a hyperbola, you actually have 2 branches. As you can see, each one of these hyperbolas has a 2 branches, and each of the branch will have their own focus. And again, the reflection property kind of works in sort of like the way it does with an ellipse, but of course it's a different shape, so it's going to behave differently. So you can see your light or sound source is coming from somewhere on the outside, and it's going to go towards this focus on the right. But then what happens is this hyperbolic shape over here is going to bounce it off. So, obviously it's not going to make it all the way to the focus because this branch here will bounce it off. And again, you will see it gets concentrated towards the other focus. So again, the light or sound is headed towards one focus. It bounces off that hyperbolic surface and gathers at the other focus. So we actually use this idea in telescopes also. Remember, we talked about the parabola and using its reflection property, but we actually use both parabolas and hyperbolas together to get even image images in a telescope. So this is actually your parabola right over here. And you can see the idea is, again, this is your light coming from, the distant planet. It's going to bounce off the parabolic surface. This is the focus for the parabola. So it's actually, again, once it bounces off this parabolic mirror, it's headed towards this focus. But right before it gets to the focus, we put a hyperbola over here. So this is a hyperbolic mirror. So, it's going to block off and it's going to stop right over here. And then the hyperbola is going to send it towards its second focus, which just happens to be right here where the eyepiece is going to be. So you're actually using the parabola and the hyperbola together to get a better image from, these distant planets, stars. And that's kind of how they're working with both those mirrors and, these telescopes. So the way this hyperbolas work, they can either open left and right, and again, the center is going to be at 0, 0, or they can open up and down. And right now, again, we're keeping. So like I was telling you earlier, the equations between your ellipse and hyperbola look the same. The only way to tell the difference is you will have this minus sign instead of a plus sign. And then again, since your hyperbola is opening left and right, the foci will fall on the x-axis. You can see we have x-intercepts at a0, negative a0. So you can see this is our focus, your x-intercept, focus, and x-intercept. We don't technically have a y-intercept in this case because your hyperbola is, crossing the x-axis and not the y-axis. And then here's the relationship between your A, B, and C values. So you can either remember this equation B square equals C square minus A square, or, so for some reason my internet is not working. So I've connected it to my hotspot. So I hope this will give us a better connection. So I apologize, guys. I'm not sure why that internet stopped working. Are you able to hear me well, or am I breaking up or anything like that? So far, it's okay. All right. It worked just fine. this past week, yesterday when I had my other class, and now it's acting up. Okay, so I'm not sure when it disconnected me. But as I was telling you, you have this relationship between A, B, and C values. What I do is just move the A to the other side and write it as A squared plus B squared equals C squared. And the reason why I like it in this form, because this looks very familiar, to our Pythagorean theorem for the right triangle. So it makes it easy for me to remember what's the relationship. And then, with the ellipse, the difference is you are doing A squared by itself on one side and then B squared plus C squared. So your A, B, and C are in the same order. You're basically, ellipses, you have the equal to after the A square and the plus is between B and C. And over here, you're basically switching the plus and the equal to sign. So it's A squared plus B squared, and then you set it equal to C squared. And that's the same thing, even if your hyperbola is opening up and down. Now look at the equation for the hyperbola opening up and down. You will notice that in this case, it's the numerator that changes. So it's nothing to do with which has the higher or the larger denominator. That's only for ellipses. With the hyperbola, if your x squared value is first, then your hyperbola is opening left and right. If your y square value is first, your hyperbola is opening up and down. And then, of course, this will change where your foci are falling, which is going to be on the y-axis. And of course, that means we will have y-intercepts instead of x-intercepts. And normally when we graph hyperbolas by hand, you actually have to kind of create a dummy structure before you can draw those branches. So this is where this idea of a fundamental rectangle comes into play. You take these denominator values of, A and B, and those actually create the four vertices of a fundamental rectangle. So you can see this is for a hyperbola that's opening left and right. Your vertices are going to be A, B, A negative B, negative A, B, negative A, positive B, negative B. So those create this fundamental rectangle. And these are technically supposed to be all imaginary structures, or, that's why we draw them as dotted lines, because they're not part of the graph. They just help us draw the graph. And then when you draw those diagonals and, extend them out, they actually end up becoming the oblique asymptotes for these hyperbolas. And you will see our branches for the hyperbola have to stay between those oblique asymptotes. And then, of course, they're going to be touching part of the rectangle where, they meet the X or the Y axis. So you actually have to draw this fundamental rectangle with the with the oblique asymptotes. And these are going to be the equations for the oblique asymptotes for these fundamental rectangles. That's the same thing you end up doing when your hyperbola is opening up and down, but, except those ordered pairs for your corners, the vertices of your rectangle will change. But it's the same idea. You draw your rectangle, take those diagonals, extend them out, and then based on that, you end up drawing your branches. And then these equations will also end up changing for your oblique asymptotes, because this is a hyperbola opening up and down. So what I have done is, I'll show you, I've created a little sort of a cheat sheet to help you guys out. So remember, if X is first, that means your hyperbola is opening left and right. If your Y value is first, your hyperbola is opening up and down. And then, again, like we saw with ellipses and circles, you can be at a center which is not at 0, 0. So this is what those equations would end up looking like if the center was going to be away from 0, 0. And I've given you, again, a couple examples to kind of help you out with what those would end up looking like. And just some examples, again, to show you, if you had some information like the oblique asymptotes and the x-intercepts, can you find the equation? Or, you're given the foci and the x-intercepts, and can that help you find the equation of the hyperbola? So just something to kind of help you practice algebraically also. So this is the cheat sheet that I was talking about, and this is available to you in D2L. You will see that, I've broken it down by each of the conic sections, so what types of equations they have. Yeah, Kayla, not a problem. Looks like we're just not having a good internet day today. Yeah, equations for your parabola, what the vertex would look like. Or this can help you find, the vertex for your parabola if you are looking at it in the standard form. Of course, if it's in the transformation form, it's easy to identify the vertex. Your focus directrix, the relationship between, the A value and the P, which is the distance between the vertex and the focus, and vertex and the directrix, both your graphs and the reflection property. I've done that same thing here for ellipses to show you the two different types of equations and how the focus x and y intercept values will change. And again, their graphs and reflection property. Your circle, again, with the two different types of equations based on where the center is going to be. And this is something that will come in handy because as you look through your examples, you will see a lot of times they don't give you the radius and you have to find the radius for your circle. And so those would be, the distance formula that would help you find the radius. And then your hyperbola again. So again, based on if it's opening left or right or up and down, the equations, and again, how your ordered pairs will switch for your focus and X or Y intercepts, depending on what it looks like. So, look through the video lectures because again, guys, this, if conic sections is something you have not done in the past, then it kind of helps to look at how those examples are solved, how to go about, breaking it down. Because some of these, I don't know how helpful that helped me solve this is. I've had some students tell me that they have gotten, just confused with that. And so I would say, look through the video lectures so you get a better understanding of what you are, looking at. So this activity actually does not take a whole lot of time. This one is just kind of introducing you to the different, types of equations, asking you to come up with your own equations for, the different conic sections. So you can stay with as simple as you like, or if you want to make it a little bit more difficult, you can, but you've got your handouts with you. You can use them as guidance. But let's see what type of equations you guys can come up with. So I've sent you the link through chat on Zoom. So you guys should be able to click on that. So try to come up with your own equations. And then I think one of those screens is like a comparison, because it asks you to pick, I think, like two circles and then talk about what you think is the same or the difference. So again, they kind of want you to think in terms of um, radius, center, just similarities and differences. Okay, so remember the first one, they just want the equation of a parabola. Elias, very nice. Yeah, I like that you went with something a little bit different. Zach, same thing, very good. So Connor, what you did is you just typed it in with, the standard form, but you want to do it with numbers because otherwise it will not recognize, the letters. So it's got to be something with numbers. So yeah, that way it can give you, and make sure one of those X has a square on it. And then Colton, Kayla, Sarah, yeah, very nice. Michael, very good. That looks perfect. Connor, did you mean to put an X next to that 4 in your equation? Janet, you might have to do Y equals because looks like your graph didn't show up. There we go. Alrighty. Yeah, and the next one on screen 2, they're asking you for a circle. Sarah, that looks good. Kayla, I think because you just did it as R square, it's not recognizing the radius. And you can actually just put, like, Sarah, you have 6 square in there. You can honestly just do 36. But obviously you saw that 6 square also works. Connor, that looks good. Zach, yeah, you need to have something on the other side. Additionally, Zach, your y minus 2, the square needs to be outside. You've put it on 2. I think you probably meant to put it outside the parentheses. Yeah. Colton, that looks good. Very nice. Elias, very nice. Michael, you got it. Very good. Kayla, that looks good. And yeah, there you go, Zach. Very nice. Nicely done. Okay, let's see. Okay, Sarah, I don't see which 2 circles you selected. on the third screen. Yeah, Kayla, very nice on number 3. Yeah, Elias, they have the same center, but then what about their radius for number 3? Yeah, so Colton, you're talking about the center and the radius. Yeah, the center will be the same, but then the radius on those two will be different. Yeah, very nice, guys. Good explanation on number 3. Yeah, Michael, very good. Janet, very nice. Connor, yeah, very good. Looks like most of you, it's interesting how most of you went with the center one. Um, and I think Kayla, you were the one who used the same size circles, but just in different locations. So yeah, very interesting. All righty. Okay, then we're moving on to an ellipse, which is on screen 4. Sarah, yours looks more like a circle to me than it does an ellipse. Because remember with the ellipse, you have the denominators on your x square and y square values. Kayla, very nice. But yeah, normally like you did equal to 3. And you can see how that kind of stretches out your ellipse a little bit. Normally we just set them equal to 1 and then you can kind of play around with your denominators. Michael, that looks really good. Elias, very nice. Colton, very good. You moved it away from the center. I like that. Looks good. Connor, very nice. Nicely done. Okay, Sarah, yeah, that looks more like an ellipse now. All right. Very good. Yeah, so they're having you do the same kind of thing on screen 5. But this time they're asking you to find 2 ellipses that could potentially have that equation they're giving you. Janet, that looks good. Your ellipse, very nice. Okay, so I'm looking at screen 5, trying to see which ones you guys have selected. And Elias, that looks good. Yeah, so you actually have to see where that center, that's coming from the x minus 5 and y plus 5 on the numerator, where that center should fall. And then remember with ellipses, you have to look at the denominator. If the larger denominator is under x, it's the horizontal major axis. If the larger denominator is under y, then you have the vertical major axis. So you again have to be careful about, which orientation your ellipse is going to have as you start choosing them. So yeah, Elias, yours looks good. Let's see, Sarah, yours looks good. Yeah, very nice. Good explanation there. Let me see, Colton. I think you're still typing in. Okay, I'll give you guys a couple minutes because it looks like some of you are still working through number 5. So all right, let's take a look here. So again, guys, keep in mind as you're working through that number 5, where is the center for your ellipse going to fall? Because remember, with these, where you see x minus 5, the minus means that 5 itself is a positive number. So your x value for the center is actually going to be positive 5. And when you see y plus 5 in the parentheses, that means it's y minus negative 5, which means the 5 itself is a negative number. So your center for those ellipses is actually going to be positive 5 and negative 5. So positive 5 for the x value, negative 5 for the y value. So when you think about positive 5 and negative 5, what quadrant is that going to be? And based on that, you should be able to pick your ellipses. So Sarah, Elias, Colton, you guys were in the right um, ellipse. Michael, I can see you in 4th quadrant. Okay, some of you are in the first and third quadrant, it looks like. Okay, Sarah, Kayla, Elias, those look good. Connor, that looks good. Colton, very nice. This is for number 6 that I'm looking at. Okay, number 5, Michael, that looks good. Okay, so if you guys will actually just wrap up with screen number 6, because I just want to see what you guys come up with for your equations for the hyperbola. Michael, that looks good. And remember with hyperbolas, depending on whether you put the y variable first or the x variable first, that's how it, decides if it's going to be opening left and right or up and down. So it's nice to see how some of you have gone with either x first or y first. So it gives you, a good example to see if it's going to be opening up and down or left and right. Zach, very nice. And number 8 screen is kind of interesting because they're actually giving you a couple points on your graph, and then you have to try and draw, your conic sections, trying to go through at least one of those points, even if it's not all, not both the points, but just one of the points at a time. Janet, very good. On number 6, that looks nice. Yeah, so great job, everybody. Looks like you all were able to draw, a good size, good type of hyperbolas with both the branches showing. So that's nice. Okay, so yeah, I'm seeing as you guys are kind of working through that screen number 8 to see how you are trying to, draw the different shapes and hit one of those points. So guys, we're actually going to stop right here. If you want to try working on number 8, you can, but actually one of my mom's nurses is here to check up on her, after she got out of the hospital. So I need to go visit with them. But if you guys have any questions, please let me know. Don't forget to request your password for the exam. And then remember, going forward, we are going to start reviewing for the final exam, but this is a great chance for you to try and get caught up on any older exams if you have not had a chance to do that. So shoot me an email if you have any questions, and I will see you on next Tuesday, guys. So be careful, stay safe, and have a wonderful week. Take care, everyone. Be careful. Bye-bye.